It's our pleasure to welcome today Claudio Bombardelli. Thanks for coming and being here and sharing. Claudio received his PhD in space science by University of Padua back in 2005. Then he moved for a postdoctoral fellowship to Harvard Smithsonian Center of Astrophysics, where he stayed 5 years and then moved back to Europe to the European Space Agency for a couple of years. And then he got a Ramon y Cajal Fellowship and joined the School of Aeronautics in the Polytechnic University of Madrid, where many of us have studied, where he's now associate professor. His main research interests are on aspects related to orbital mechanics, space mission, space awareness, including space debris removal. Indeed, he's the inventor of the ion beam shaper, which is also part of the title. So I guess he's going to be telling us about this for contactless space debris removal and asteroid deflection. Right. So quite interesting topic. And well, thank you very much again. Floor is yours, Claudio.
Thank you, Manuel. Thank you for inviting me. It's a great pleasure to be here. Although sometimes I'm here because we have a very good collaboration with the group of Eduardo Aedo and Mario Merino. And also with hopefully with Gonzalo, who's going to be involved in research activities. This talk is mainly completely focused on this IBS concept, the ion beam shepherd. It's about contactless actuation, basically what we can do with this apparently crazy idea, but which eventually works. Is to move objects around, and the main two classes of objects we are interested in are space debris, possibly active spacecraft as well. We're looking at that too, and asteroid. The advantage is that we are moving things without contact, and of course, we can get away from all these risky aspects of robotic interaction, mechanical interaction, and so on. First of all, I would just like to give you an overview of what we're talking about. Maybe you've heard about it, but let's start from scratch. What is the IBS concept? The idea is to point the ion beam of an ionic thruster that can be typically an ion engine, but it could also be a Hall effect thruster towards a space object. The ion that are emitted by the let's call it the impulse transfer thruster, this thruster here, reach the target and penetrate the substrate of the object, whatever object it can be, and transfer their momentum to eventually produce force, a contactless force that can be used to move around the debris or the asteroid. Of course, you need another propulsion system, typically another engine you can think about as a similar engine that the other one to keep the Shepherd spacecraft from drifting away from the target you're actuating on. It's a contactless method, and that implies low risk, especially when you have a robotic alternative in mind. Main advantages, I divided them into two classes. Let's suppose that we are using it for debris removal. The primary advantage is the comparatively low risk. You do not need mechanical contact. You have a safe operation distance. Typically, what you have in mind is 10 meters, but it could be a little longer. You can play with the distance efficiency trade-off. I'll go into more details later on about this aspect. The other key advantages is that we are target agnostic, meaning we are not influenced by the geometry, mechanical properties, shape, and material of the object we like to move. It's the other key aspects, reusability, is connected to the target agnostic aspect, advantage, in a way that if we move one object and we have enough propellant, we can do the job, move towards another object, do the job, move to a third object, and repeat this. So with one mission, if the objects are in nearby orbits, we can do a lot of things, and that's quite an important advantage. We have maneuverability and efficiency. Since we have electric propulsion on board, we have a high specific impulse, and we can move around with very low propellant consumption. And last but not least is the technology readiness. The TRL is very high in terms of at component level, because we have been flying ion engines and Hall effect thrusters. They are mature. They can be improved, but they work. Of course, the TRL, if you can see it as a system level, that's lower because we have not assembled yet an IBS and perform a demonstration mission. So that's remained to be done, but hopefully it's going to happen soon. As far as asteroid deflection, similar advantages are to be considered. First of all, the transmitted momentum is asteroid independent, is the target agnostic advantage that we've seen before. Then we have a gentle handling of the target, which is key when you try to deflect asteroids. I don't know if you know a little bit about asteroid deflection, but what we've been doing so far is to do it by kinetic impact. You slam a spacecraft against the asteroid, like in the DART mission, and the momentum that is transferred in a very violent way. This is acceptable as long as the asteroid is not too small and could break apart. And if it breaks apart, you do not want to create additional risk because you don't have control of the fragments. They could impact the Earth. That's key. Then you have bidirectional and accurate deflection. This is a little bit more subtle. The kinetic impulse can deflect the asteroids only in one way, because you cannot only slam against it, you cannot break it. So that's advantageous in terms of choice. You have more efficiency. You can move it in two directions with respect to the path of risk of the Earth, and it turns out more flexible. You have a reconnaissance capability in a way that if you are deflecting an asteroid with an IBS, you need to rendezvous with it. And if you rendezvous with it, you can do many interesting and useful things. You can improve the covariance of the asteroid orbits. You can analyze the shape and estimate the mass, possibly characterize the asteroid, and you can do that during the deflection. So when you are deflecting it, you can accurately measure how much you've deflected. This is key in planetary defense. Last but not least, scalability. If the asteroid is huge and you need a lot of delta V, you can think of having multiple IBS acting on the same asteroid at the same time. It's a little bit more complicated, but it can be done. So these are the advantages that motivate the analysis and going into more details in terms of modeling. How do you model this? At the beginning, we didn't have a clue on how to start with, and we started from scratch, and we built a lot of analytical and numerical methods, and I go through all of them in order to give you an overview and some key equations. The first thing that you have to do is to choose your thruster. Now, here many of you are big experts in electric propulsion, so nothing to teach you here, but it's important to consider. The key aspect is divergence. You want a low divergence beam because you want all your ions to hit the target without having to be very close to it. So the lower the divergence, the farther away you can stay from the target, and the less risky your mission becomes. You want high specific impulse to save propellant mass. You want long lifetime to be able to push for a long time. And of course, a high TRL device. So your choice in this case is probably high voltage gridded ionic thruster of the Kaufman type, similar to the Bepi Colombo T6. It's a good thruster. they're having problems, but that's maybe related to power. I don't know if you heard, but let's hope that everything is going to go according to plans. But you have other thrusters in the American side, the next thruster that propelled the Dawn mission and now the Psyche mission. So you have options. However, it's important to consider that you can put a trade-off on the table with the Hall effect thrusters, which are the main huge expertise here, because the Hall effect thrusters are simpler and they need less mass around it in terms of power, PPU, to make the system work. So for a demo mission, in spite of the fact that Hall thrusters have a much larger divergence, you can get away with efficiency, lose a part of your ions, and consider this simple thruster as a demonstration mission. Second thing you have to do is to model the thruster, and these equations, most of you are familiar with this, so I go through very quickly. You choose your beam voltage. Let us assume we are designing with an ion engine Kaufman type. You have a whole bunch of efficiency, mass utilization efficiency, the propellant that comes out as ions, the electric efficiency, how much power it really becomes beam power, thrust efficiency that characterize all the thrusters, and the main input, of course, is the power that you can afford. So once you have all that, you can compute the specific impulse, you compute the beam current, and you can compute the force that you are able to produce, the thrust you are able to produce, given the power and voltage current that you are allowed to use. And the thrust efficiency, you can write it in terms of specific impulse and force and like that. Once you have these key equations, then you start going to beam modeling. You need to analyze the beam and see how you can model it to deal with its main characteristics and eventually extract the force that you can transmit. So the key facts is that the ion density of a beam cross-section follows with good approximation a 2D axisymmetric profile that simplifies modeling as long as we are sufficiently far away from the thruster exit. We can say that we are Gaussian, and you can define the size of the beam by taking an envelope containing typically 95% of the beam density. And the key aspect here is that the beam will expand as a funnel, not as a cone, unfortunately, because apart from the near-field divergence that you are all familiar with, there is an electron pressure effect, thermal effect, due to the temperature of the electron that slowly makes the divergence increase. And this is key, especially for asteroid deflection, where you have to stay quite far. If you stay at 3-4 asteroid radii, that's already half a kilometer, maybe at least hundreds of meters, and this effect has to be kept in mind, let's say. Another key aspect here is that if you want to reduce this divergence, at least for an ion engine, the main parameter is the specific impulse. You shoot out ions faster, and you expect that you are more collimated. And that definitely is beneficial in reducing divergence. Going into more details into how you model the beam in order to then extract the force, you have a density. You remember your axisymmetric, so you have a radial and axial direction here. You want to know what density you have at a specific point around the beam. The profile is Gaussian and is influenced by the divergence. In this way, the velocity can be that's important fact, can be modeled as a conic velocity, so you can neglect the funnel effect there and can be very accurate. And The key parameter here is the divergence of the beam, the near divergence of the beam, which is theoretically a function of the ion temperature with this formula here. Why did I put this form? Sorry, something not working here. But why did I put this formula B0 minimum equal arctangent of? It's because somebody may think about reaching a zero or near zero divergence and then pushing things from the moon's surface around the solar system, something like that, like this futuristic. Unfortunately, there is a minimum divergence you will always have, and no matter what, how you are able to construct your thruster that is summarized by that formula. And if you go into the far field, there is a very useful formula, the Ashkenazi-Fruchtman, which allows you to generalize the divergence by taking into account the Mach number of the electrons, and comes here, and this is the funnel part of the beam. So you are increasing your divergence a little bit more. Of course, this can be refined as approximate relation. So if we summarize the divergence with this formula, it's clear that you need high specific impulse, as I mentioned before, but also you need to reduce the temperature of the ions and the temperature of the electrons, so neutralization and mixing of the electrons with the hollow cathode. These are clear aspects that can be played with to improve the divergence of the beam. You want a cold and collimated beam, basically. What can be achieved? This is a low divergence optimized thruster that was built and tested in the low sweep project we participated in together with Carlos Tercero, the group of Mario Merino. They built a low divergence 3500 volt ion thruster with 3 grids. They put interestingly the hollow cathode in the middle to get a better neutralization, and they achieved a 4.1 degree near field divergence. That was quite a good result for that specific impulse. But I'm sure that other ideas can be put on the table to reduce the divergence even more. Now, another key aspect of the concept is the beam-target interaction. What happens when the ions strike the target? The fast ions reaching the target do not bounce back, as you perfectly know. But if I have to explain this to orbital mechanics, that's not so obvious. So they penetrate the material substrate, they lose energy by elastic nuclear collision, primarily given the voltage we are playing with, kilovolts. Secondary inelastic collision, which is electronic stoppings, is probably negligible and get implanted in the substrate at shallow depth, nanometers. So the conservation of angular momentum can be written there. But if they stop, you have a force arising that pushes the target. Now, the ions stop in the substrate, but there is stuff that comes off of the target, which is the sputtered atoms of the whatever material is the target made of, or cluster of atoms that are emitted at much lower energy. So it's not like they come off at 60 kilometers per second. So that means that it's not like you get double the force or considerable extra force from it. So you can neglect that. This sputtering jet would produce a negligible force. How do you eventually compute the transmitted force to a target of arbitrary shape? You integrate and you discretize. You cannot do that analytically if the shape is complex. And the force can be written as this integral. The first part is a classical fluid mechanic formula you've seen all the time. But I like to put it into this less fluid mechanic formula that is more related to the nominal force F0 of the thruster, you're using the divergence beta and the distance z from the beam source. And of course, you have the tangential and unit vector of the beam ray and the normal unit vector of the piece of surface you are considering. You have to integrate along the surface and get the force. You put this into a software, and it at each integration time gives you the force, and you get the torque, and you can start simulating things. In that software, it can get more complicated if you have non-convex shapes. You need a ray tracing. That can be done. It's a little bit more programming effort. We've been building all these software tools, but in parallel to those tools, to purely numerical tools, you need also simple models to really help you design the system without having to run simulations. And one good thing was the cannonball model. If you consider a spherical object, then you can go and integrate things analytically, or at least semi-analytically, by doing a little bit of geometry. And so these are so basically a force that you can get here is the force that pushes the disk that is cut by the beam flow here. And you can forget about the sphere, and you can only consider one surface. If you integrate on that surface with this Gaussian beam, you get these integrals here, the normal and transversal, then they project it into the reference system you want, and you can get analytical formula. If you expand this for alpha very small, alpha is the angular position from the beam axis, then you can really get truly analytical formula you can use to design both your system and your control, as I explained to you in a moment. So you can get to this nice formula here that tells you the beam momentum transfer efficiency. What's that? That's the force along the beam axis that you can get compared to the force that your ion engine is producing. So you don't get as much as having your ion engine mounted on a debris. You get a little bit less simply because some ions miss the target. And you can get this formula by integrating the Gaussian profile onto the debris, and this is the exponential formula eta b that we use all the time. So you realize immediately the trade-off here. You have the choice of how far from the debris you are actuating and the efficiency that you can get, and the divergence of the ion engines. So if you are able to produce a 7-degree divergence, half cone divergence, then you can get this very nice efficiency even if you stay at delta is the non-dimensional ratio between the distance and the target size, the sphere radius. So you can stay at, let's say, 15 target size, could be 30 meters from a 2 meters object, and still have some 70 to 80% efficiency. Of course, you can start using a Hall effect thrusters that is here, then your efficiency forces you to either stay very close or accept a lot of more propellant consumption. Sputtering, why is sputtering critical? Not for the force that we produce, but for target erosion and contamination. You do not want your target to be completely destroyed, or maybe you would love to have that, because some debris would enter the atmosphere in a different way. But we have not played with that idea, but let's say that you want your target to stay mechanically, structurally solid. And then, even more important, you do not want to have all this sputter material back polluting your sensors or your solar panels, so that that could be problematic for the IBS. So the back sputtering is an important aspect, and of course, you can imagine the farther you go from the target, the less sputtered material you get. So that's quite important. That goes down to reducing divergence. No? How do you design a preliminary design of the IBS? First of all, you size your thruster because you want to get some numbers for how much power, thruster, force you need for doing a specific mission. You are given a target mass, you are given an initial orbit that I find it convenient to model by the orbital period. Let's suppose that we are quasi-circular, as most of the debris we want to remove. You have a descent or ascent ratio, H dot, 1 kilometer per day, for example, that you want to have in order to make a mission sufficient fast. I don't know what the tether can do with that. We can do several kilometers per day. So suppose that you're playing with those numbers. You target a specific target transfer efficiency, depending if you're a demo mission or if you're a multiple removal mission, you want to have a high efficiency and so on. So once you have all that decided, you can finally get what nominal thrust you need, the ITT, you see the orbital period plays here. You may think, why is not a factor of 2 there? But if you think about Lagrange planetary equations, you have the one of the semi-major axis got the 2 in the equation, so that gets simplified by 2 or divided by 2 pi. And so that's very simple. And you need to size also the impulse compensation thruster on the other side. That depends on the very simply on it's a static equation condition, equilibrium condition, and depends on the efficiency and the mass of the IBS and the mass of the target. Then, once you have that decided, you want to estimate, and this is crucial, how much will your IBS weight for the debris that you're displacing. And that depends strongly on the power you need. The power is crucial there and can be estimated based on the force that you're employing, both for the ITT and the ICT. And of course, that force depends on the H dot. So there are this simple equation, compact equation. You get a formation equivalent mass. And the fuel, it's simple to estimate based on the force. And you get a total mass that is power density, power of you need for the propulsion, the structure mass, and the propellant. Example, Hubble rescue mission. I'm personally convinced that the key challenge in space debris removal is not moving the METOP or MVSAT. I think we are wasting time there, but we have a much more urgent thing to do, which is making sure the Hubble that is 12 ton and is at 520 kilometers altitude does not get into the atmosphere in 10 years from now or 15 years from now, which is the current estimate. And if we could just boost its orbit above Starlink shells and get 100 years lifetime, that would be great to then go with a robotic mission. So I think it's a good opportunity for the possible IBS mission. And so let's suppose we want to do that. So move out Hubble by 50 kilometers up in 4 months, say. So you assume no thrust during eclipses, 25 meters separation, specific impulse 3000. You suppose that you're not too picky with the efficiency, you accept 50%, thrust efficiency of 60%, maybe it's too optimistic, but power density 15 kilograms per kilowatt. So the results is you get some margins, structures, RCS mass for proximity control. So maybe possibly you can do it with a 350 kilograms spacecraft, which could be quite good. How I'm going with time? Strict. Okay. So the other thing, once you design this mission, is how you control it. This is the big challenge. You need to ideally have your IBS here and your target always perfectly aligned with the beam axis in a co-orbital position, so tangentially to the orbital direction. So the target center of mass lays on the beam axis, and the beam is perfectly aligned with the orbital velocity, and the distance is constant. So that is an unstable equilibrium configuration. I will show you later. So you need a 3-axis RCS control to stabilize this. And you don't know where the center of mass of the target is. You know the shape, so you may have to play with the visual recognition and a delicate guidance and estimation hardware, so LiDAR and so on. And in all this game, the fuel that we'll need to keep this thing controlled will be critical, because you probably do not have an RCS that is electric propulsion based. It's probably hydrazine or gas thruster. So if you can really minimize that force, that would be crucial for the mission. So how do you write this down? You ideally want to have the classical proximity formation flying equations, the Clohesi-Wilshire equations, with an additional ingredient, which is the beam force that acts on both the thruster force on the shepherd and the beam force on the target, which comes here. And of course, you have a control strategy of your formation along its orbit, and you have attitude of the target that obeys Euler equations with a torque that is not just the environmental torque, the gravity gradient, and so on, but also the beam torque. So all of this has to be put into your model. Nice thing to be able to control this is to get the beam force as easily modeled as possible with some approximation, and we came up with this beam gradient tensor or matrix, if you project it in the right direction, which is similar to a gravity gradient tensor, but with the beam force. And if you consider a cannonball model due to axial symmetry, you can have a very simple shape of this beam, of this tensor, this matrix, where you have this parameter B, which is just function of the efficiency and the divergence, and is positive. So if you are able to model things like this, a tensor is a linear element, mathematical element. You get a linearized equations of motion, and you can get stability. You can design your control in a very proper way. And then you can try out that linearly designed control in a fully nonlinear system, and with all the software, and probably things are going to work well. If not, you complicated the design a little bit. So what we got is this beam perturbed Clohesi-Wilshire equations. I don't know if you're familiar with this. This is relative motion equations. If you take away this coefficient gamma, you get the Clohesi-Wilshire equation that I like to write in non-dimensional form, just taking away all the orbital mean motion and so on, and non-dimensionalized with respect to the target radius. So you get this form here, and this gamma parameter is crucial because it's the beam part, and the beam part can be related to this B coefficient that I showed you earlier, the efficiency, the force of the thruster, and here you have the mass of the target, the angular rate of your orbit, and the thrust, the target size. It's positive non-dimensional coefficient, the one that all engineers look for, the one that tells you everything, and like Navier-Stokes, like the Reynolds number. So what does it tell you here? It tells you that if you are in either you are a beam-dominated regime, the beam is stronger than the gravity gradient. That's geo. If gamma is much less than 1, you are in a gravity gradient dominated regime. That's Leo. So that tells you that if you need to design a control for a geo mission, the beam plays a quite important role. So you oughta model it more accurately. Stability, I don't know how much time I have, almost done, but stability, you want to see how stable that formation flying problem is. You rewrite the Cauchy-Wiltshire equation in this compact form, in matrix form, where S is your state vector, and you have a stiffness matrix and gyroscopic matrix, Coriolis matrix. You get the linear stability analysis, and you see immediately that the in and out of plane are decoupled due to the symmetry, axial symmetry of the beam. The out of plane can be made stable if gamma is less than 1, but the in plane is always unstable. It's always going to have a real positive eigenvalue, no matter how you play with gamma. That means that it's not possible to design an ion beam formation that is naturally stable. You need control, expectedly, no? And if you start designing your control, the first thing to do is to keep things simple. You write a PD, proportion derivative control, playing with the relative position of the target with respect to where it should be. So x dot, y dot, z dot. You plug this stuff here into the relative motion equation. To cut a long story short, your stiffness and gyroscopic matrix get a little bit more complicated. Some gammas appears there, which gammas are characterize the control and your controlled gains, basically, the PD gains. And same for the gyroscopic matrix. That becomes non-diagonal, crucially. You get the stability condition, and you choose your controller gains in such a way that you're stable. You can do that, and then you can optimize the control gains to get it very effective in controlling the relative motion. And these are some results that we obtain with the Leo sweep. In the Leo sweep project, you put the target here of the beam axis, you plug in your control, and your control is gonna bring it here where you want it. If you zoom up, you can see a little bit of motion of the target around the equilibrium position, because you have perturbation. You have a J2 gradient here. It's a initial zero eccentricity orbit, and you can see here the force of your thruster, of your control thruster, how they evolve. You can see that they are not going to 0, but that's because not necessarily this the distance that you got from that you wanted to reach from the target is the optimal one. So then you can decrease that distance, trying to make this residual control force to 0. And you can see the efficiency from 20% gets to the nominal efficiency you get here. You can try this with a elliptic orbit, a little bit more elliptic orbit, and you get a little bit of complex motion around the equilibrium position associated to the fact that it's more difficult to control relative motion along an elliptic orbit, and you have oscillation and so on. We're done with that 1 ton debris, 2 meters radius in a control trajectory with respect to the IBS. The IBS is 300 kilograms and with 100 millinewton thruster towards a nominal 10 meter separation. And I think with that, I'm done. So just to wrap up, IBS concept has been introduced together with the main physics behind. Hopefully I give you a connection with the math of the problem too, in a simple way. We have motivated its use for IBS and debris removal and asteroid deflection. I mentioned propellant efficiency, reusability, and adaptability as strong merits for the concept. Introduce design criteria. Simple equation can be used to start modeling things and see if the concept is actually promising, starting from the mass needs point of view. And of course, relative motion is, in my opinion, the key technical challenge, and we need to, but it's going to be fun to design this for a demo mission, hopefully to come soon. With that, I'm done. So I'm ready for taking questions. Thank you.
Hello. So thank you very much, Claudio, for your presentation. I think hopefully it was quite inspiring for the students to have an idea and then do all the design, physics, modeling, dynamical system control, eventually going into manufacturing and flying at some point, right? I think that's quite interesting. Questions? Gonzalo, I know you have to go fast, so go first.
Exactly. So I have to leave in a few minutes before I leave. Now the in-orbit servicing market is supposed to grow a lot. There is a lot of interest on that. I wonder if you catch the attention of Clear Space, ExoTrail, and all these companies. They are supposed to do this type of things because the concept is promising for them.
Yes. The key aspect there is that we would love to be in that business, and we contacted Astroscale, for example, for that. The key is to convince them that this is not just to D-spin, because at the beginning they love it as a D-spin device, and then to go robotically with their capture mechanism. But I think that a very promising avenue to go through is to be able to do servicing with the ion beam on an active spacecraft without robotic interaction. And the key is to assess whether the beam irradiation is damaging the spacecraft or not. We think that, and of course there are experiments to be carried out, but we think that with a kilo electron volt beam, and especially in GEO where you need a little bit of thrust to just reach graveyard, we're talking about 5 meters per second, that's not much, to move things around in GEO, maybe we can do it with a very little beam irradiation, and we can do it with an active target with no big issues for its. Of course, the advantage there is that you can go to a target, let's say, do the north-south station keeping for it, and once you're done, and this is done maybe once per 2 weeks or once a month, you can go to another target, move around the geo ring, and do more. This is something that the robotic system cannot do, because typically it's attached to the target, it does the control, and it stays there. It's not. I don't think they are considering a robotic system that attach, detach, go around, attach, detach. That's risky. So hopefully we have an interesting opportunity there. We'll see.
Okay, my second comment is the specific input you are using. I thought for ion engines it would be higher. No, you are using. I think you are using modest values. No, at least
true.
I found higher values in Wikipedia.
Yeah. No, that's. I mean, you could use lower impulse depending on the power trade-off.
So you were conservative on that.
In that case, the especially in LEO, you didn't want your power system to become too high, and eventually you get a heavier spacecraft. especially at for a demo mission, for example, you may want to reduce your power system mass as much as possible and be able to get a beam. I don't know if Mario has more to say about that, but my feeling is the ion engine pays a higher price in terms of power consumption than the Hall effect thruster, and the PPU is a nightmare. No, although now they are trying to design modern stuff. So
Also the trade-off between the power system mass, the mass of the propellant, the time that you need to the orbit, so the thrust specific impulse is a trade-off there.
for example, there is a just to give you an idea. Do you know the DS4G thruster? There was a thruster that was developed just to beat the record of a specific impulse at the European Space Agency, and I think that they got to 12,000. That was the record. It was 4 grids, but that thruster is useless because with that specific impulse, the power you need is so huge that then propellant becomes like a secondary thing. you waste maybe in an interplanetary mission, you waste 50 kilograms of propellant to go very far, but the power system weighs like 4 tons. so that's the key of the trade-off. At some point, you do not want a specific impulse to.
Okay. Other questions?
There is a question from a student there. Yep. Well, student, or maybe as a professor. I don't know. He's a professor. He's already. Sorry.
That's okay. Can you hear me? Okay. Okay. I had a question about the Hill Velocity Welchar recursion HCW that you showed on slide 23, I think.
The non-dimensional, this one?
Yeah, this one.
Yeah.
So I think this is the modified version of the original HCW. But then in your results, you had the eccentricity of 0.05. I think you used a small eccentricity value.
Yeah.
Did you consider maybe using the eccentric extensions of the HCW? Because I think there are modifications to HCW that assume a small eccentricity.
Good questions. So the initial approach was if you think about small eccentricities, not probe emission or anything like that, just the main RSO's eccentricities are very small. So the idea was design your controller with a circular model and see if you can cope with a small eccentricity model, and it did. But you're right that it would be interesting to generalize your equations to the Chalmers-Hampel's equations with eccentricity in, and see if you can get a propellant saving from that. Right. And that's a good question. And I think that's an interesting research contribution to be made in future analysis.
Right.
Yeah.
Especially as you go through the orbiting, I think because your shape is changing constantly, even though quite statically it would be like a circular, but I think because of the change in the eccentricity, it would be helpful.
Yeah, I mean, to start with, if you have an eccentric orbit and you have a formation, you have an oscillating distance that is basically the nominal distance multiplied by 1 minus the eccentricity. So if you, instead of controlling at a specific distance, you track a nominal distance, a fluctuating distance, you surely get an advantage in terms of propellant consumption. Yeah.
Thanks.
Just
and one quick question. You mentioned formation with multiple IBS modules. With that, are you envisioning treating the asteroid as your chief and the spacecraft like separately, or one of the spacecrafts would be the chief and then you would have two separate problems to look at?
No, that was the idea was to have 2 or 3 at the same asteroid and working at the same time.
So like your formation problem would be formulated as having the asteroid as your sort of the chief and then the others following it, or would you have a formation for your multiple?
No,
ideas?
it will be the chief and the others would be the
deputies.
followers. However, I must point out here that the formation flying control for an orbiting asteroid asteroid hovering mission, it's dramatically simpler than in low Earth orbit because the solar gravity gradient, it's negligible. So basically what you would have is like a free fall condition where your asteroid is here, you are here, there are no forces whatsoever, and you are just playing with a bang controller in order to keep that. So it's, in my opinion, is much simpler. That doesn't mean that is trivial, because it's a beam dominated region, exactly. So the eta prime, Zeta prime no, but psi prime would disappear basically, and you get gamma very high. So yeah, you can do a serious expansion and see what happens. Yeah.
Okay, great. Thanks, Claudio.
Thank you.
Thank you. Is there any other question, or we close the session?
Mario.
Mario, very last question.
Okay, thank you, Claudio, for the interesting talk. Okay, just a comment. The crucial part that maybe you didn't expand about is the navigation part. No, so the type of sensors, the type of algorithms. I'm just mentioning this because I think this is a very interesting problem that is very multidisciplinary. No, so there is room for a lot of work to be done, not only on the plasma side or the dynamic side, but also on the, I don't know, computer vision or LiDAR or whatever is used. No, I don't know if you have been able to progress on that a bit with the help of other groups, or what is the status of IBS missions in general in terms of
Yeah, absolutely. You're absolutely right. I would add AI. It's also possible there because think about a complex shape and an AI module that learns about the shape of the target and how it interacts with the beam in a complex way. So it's a fascinating problem. I must say that we did something. We were able to, for example, to simulate a more complex object like Envisat with ray tracing, and but we haven't got to the level of having for example, a LiDAR module model into so you're perfectly right. The next big step is the estimation part and the measurement parts to be part of this model, coupled to it, and with all the noise, all the for example, just to tell you what we've done so far, and going more in depth with this, what we did is to add some estimation nodes, Gaussian estimation nodes in different components, and see if the system works, doing Monte Carlo analysis without knowing if that noise is consistent with the LiDAR model that you have. So maybe somebody from the LiDAR would say, no, that's much better than that. But you have to contact manufacturer, and yeah, that's future. I'm very excited about it. Thank you.
Okay, so let's thank you again, Claudio.